Hey, welcome to confidence interval for the mean. What's going on here? Who's got my car out of the garage? Uh-oh, I don't think so. I don't think I could afford that, but I could afford a few wheels for it maybe. And what's this question here? What is it really? What's that? What's the mean really, I think? And of course, going back to our first presentation, can you ever actually find the population mean? Unlikely, because you have to test all the individuals. So this is the area about statistics that worries people. Can you really find it? Don't know. We're going to find out. And here's a protein bar back again. We're going to be doing some more with that. Please don't eat it before the last problem. It's well down the presentation. What's this here? There comes some computers. What's really the lifetime of a computer? What's really the mechanical lifetime? Well, how can they guarantee 3 years unlimited kilometres? How long will this tyre go for? What is the real mean of these sorts of variables here? Random variables. And here I can tell you something about the purple cow milk. I tried some last night and it isn't purple and it's very nice. So you might have trouble buying this around the place, but if you can, then it's a good product. We still need to check, is the mean protein really 39 grams? What's the chances of that 39 grams in 1 litre? That remains a problem. I'll give you a hint, mate. It's going to be a problem forever. Okay, this is random distribution, random variables here, and there's a lot of variation and estimation needing to go on. All right. Let's go and see if we can trap the mean. From sampling, can we actually get some boundaries between which the mean might lie? That's what we're about. None of us have actually ever gone and measured the population mean. We haven't got the time, or we can't waste the product to actually find the mean of the whole population. Let's go down and see if we can get our head around that sort of stuff. Here we are, of course, confidence intervals for means. It's exactly what it sounds like. A confidence interval is an estimate of a parameter. We can't measure it, we don't want to measure, or can't financially or the time measure every member of the population. Okay, so it puts the mean between two limits. I like to think of it as, let's try to trap the mean. Trap the mean. Okay. We can't actually measure all the members, but we can estimate it or trap it between two values, hopefully. And we want to assign a percentage likelihood that's actually going to be in that interval. All right, how can we do that? Well, here it is, of course. This was the important mathematical breakthrough, this probability density function, which gave rise to our realization here that within a population there's going to be random variation, and the population mean is going to be here. Okay, random variation is going to produce a normal curve, a normal distribution. Okay, and within that, of course, when we take the mean, the average of all members, we're going to be right in the middle there. It's going to be symmetrical because of random variation. Now, however, when we go into that population and we start sampling, well, it could be from anywhere, couldn't they? And this is what we're going to say now. How far out, we've been doing this for some time now, how far out do we expect a member of that population to be when we take one and form a sample? And the big thing there, of course, is we want to have a good go at this. So our samples, X bar 50, let's take not just one, let's take 50 and find the mean. And that's going to help us zero in on the actual mean of the population. Just sampling one or two won't do. Let's take a bundle and find their mean. And the central limit theorem was important in that, because we know that those means will be distributed normally. The same mu and a sigma on root n. We have some tools now. Driven, this unit of work in inferential statistics in this little course, is driven by the central limit theorem. It's all about the estimation of the mean, the average. I say you'll get 40,000 kilometres out of this set of tyres, or you can have 100,000 kilometres guarantee on your mechanical parts in your new car. How do they do that? How come they don't go broke with such guarantees? Okay, and so let's have a look now at how we can work out how to trap the mean and how to work out the percentages that are likely for a value away from the mean, so that we can offer guarantees and things to people. Okay, come on down and let's have a look now at this little dude here. Of course, this is the mummy or daddy of them all. This is the standard normal curve, or the probability density function for the standard normal curve. And I haven't written it in there though. Z is normally distributed, a mean of 0, and a standard deviation of 1. There it is. And on that curve now, what have we found? What are the values from neg A to A, which have 95% of all scores between them here in this population? Well, I think you know from our hypothesis testing in the last presentation that that is 1.96. Here we are. Okay, we'll just come down here a little bit, and if you found those values with an inverse normal calculation, you would find that it's 1.96 and neg 1.96. Okay, so what does that mean for a distribution of means? Now, if x is normally distributed, then its mean will be normally distributed and its standard deviation will be smaller. And by the central limit theorem, if n is sufficiently large, x bar always, even if it comes from a non-normal distribution, will be normal mu sigma on root n squared, won't it? Okay, so it's quite clear if you're taking from a normal distribution, any samples will be normally distributed, and the means will be narrowly distributed, more narrowly distributed. But the central limit theorem to the rescue. We do not have to prove that the original population is normally distributed, as long as n is sufficiently large. Okay, so what have we got? What's the property of this normal distribution? Well, we've got a central value, a mean, and then we just said from the standard normal curve that 95% lie not two standard deviations. Here's a standard deviation, isn't it, for x bars? This is the population of x bars here. Okay, so here in the x bar population, when we take means and plot them, the variation, standard deviation is this. Okay, sampling error or standard error, the deviation of our sample means away from the actual value, their error in what that we're making in trying to estimate this population mean here. Okay, so how many have we got? 1.96. We actually told a fib before. Remember when we were doing the approximate stuff with a normal distribution, we were saying that there's the mean and one standard deviation either side. That's still correct. We proved that one is about 68%. And then we said mu plus approximately 2 sigma. And mu take 2 sigma gave 95%. This is more accurately now stated as 1.96. As we get down to calculations could have legal ramifications, because this 95% confidence interval or 5% hypothesis testing at a significant level of 5% is legally able to be quoted in courts and so on. So we want it fairly accurate now, so we're going to go 1.96. So if you check that on the standard normal curve just from up above there, and you want here those limits so that you have 95% in there, check, put in lower neg 1.6, upper 1.96 on a mu of 0, sigma is 1 standard curve, and you will get very close to 0.95 in there. Okay, so we're modifying it now, just a little. Okay, so when we sample from this population of sample means, if we took all of the sample means, then their mean would be centred around the mean of the original population, and the x bars would go between this and this with 95% confidence. Now, in other words, some by chance will lie in the wings by chance here in our sampling, but 95% of the cases, the X bar should lie within that interval, shouldn't it, from our theory so far? Okay, so when we sample, our mean should go between those limits. And of course, that's the same basis as the hypothesis test. Okay, we say, looked at the two tails, and if between them they didn't give us 5%, we rejected the Z-score at that 5% level of significance. So it's the same idea. This is a less formal treatment. Okay, and it can be used to assess claims about the mean, and we're going to do that. Okay, are you getting your head around this? This variation is the problem, isn't it? We can't nail it. What is it really? What does that mean really? Don't know, never will. Okay, we can hunt it down though. Let's go on our mean hunt. That's pretty mean. Okay, here we go. Let's do some maths. Okay, so here's our distribution of our population. Okay, showing random variation here. And even if it didn't, of course, our means would be normally distributed under the central limit theorem if n was sufficiently large. So what we just said here is this is a 95% region. This is one standard deviation above the mean, one standard deviation below the mean of the original population. And we're grabbing samples, X bars, and grabbing them from various places. And what can we say? We have 95% confidence that the X bar we grab from the population will be the mean plus 1.9 sigma or mean minus. Now, this little creature here is actually by chance outside of the region. So it is possible from our random sampling, only with a 5% chance there and here, 2.5% in the wings, there is a possibility that you will grab one that is outside of that. But there's only a 5% possibility, 5% chance. So that's our level of uncertainty, if you like. We're 95% certain that our X bars that we sample from this population will lie in that region. So let's have a look. Let's unpack it. Let's take this thing here and subtract mu from that part of the inequality, and we get this statement. And if over here we rearrange this part, mu take 1.96 sigma root n is less than X bar, then X bar minus mu is greater than neg 1.96 sigma on root n. Now what are we doing? What are we doing? What are we doing this for? Do you remember we're hunting mu, the actual population mean? That's what we're hunting. We're trying to trap mu. How cruel. Trap mu. Okay, so over here let's rearrange this. Putting mu on the other side, adding it. Mu would be less than X bar plus 1.96 sigma on root n. We're over here, rearrange it. Mu would be greater than X bar take 1.96 sigma on root n. I think we have done it. I think we have located the region which can contain mu, remember, with 95% confidence, because we are confident under the normal distribution theory and central limit theorem that the mean will be within those limits. Okay, come down, let's formalise that now. Here it is here. So in other words, mu will be trapped between the mean, the sample mean, plus 1.96 sigma, which for X bars, remember X bar is normally distributed with a mean around the actual mean of the population, a standard deviation of sigma on root n squared by, well, if the original distribution is normal, so will X bar be, but even if it isn't, central limit theorem, if n is sufficiently large. Okay, and what's the other limit? We have trapped it. This is a mu trap. Okay, so we have trapped mu between these two values. But we've got to go out and get an X bar. Okay, go to the population, sample it. So here it says if we're able to take many samples of size n, calculate the sample mean. Why do they say many samples? Well, then we don't have to prove that the original distribution is normal. Here it is here. Many samples ensures that sufficiently large size, and therefore by the central limit theorem, X bars will be normally distributed around mu, and we can trap it. This is a mu trap. Okay, then for about 95% of these sample means, so It's only approximately, because approximately normally distributed. The population mean mu would lie in the interval. We have trapped it. So, is it getting exciting? We can actually test claims about products. Okay, you could go out and do your own project, actually. Sample from the supermarket shelves some of this purple cow stuff. Oh, you could have trouble finding that, mate. Anyway, sample from the supermarket shelves and weigh or measure whatever you're trying to measure, and then look at the probability that that is correct. The claim on the packet of a certain number of grams of protein or something is correct. This is powerful stuff now, and it is used by Consumer Affairs under the Trade Measurement Act to actually determine whether the product is being sold properly or the claims are being made legally. All right, let's do something with it. Okay, so here is the result. And again, these screen clippings are from Hayes and Harris, so it's handy to have their textbook or an e-copy of it would be good. The 95% confidence interval for mu lies somewhere 1.96 standard deviations, which is sigma on root n, above the sample mean, down to 1.96 standard deviations, which is sigma on root n for the mean, below our sample mean. So that's what we're saying here. There's our sample mean, hopefully with pretty large n, so we can ensure approximate normal distribution under the central limit theorem. And here we have the width, and we could calculate those values. Okay, in run mode on the calculator. I'll just give you a little secret. Later on I'll tell you how to do it with the calculator, with a program on the calculator. Okay, but we'll do it by hand at the moment. A sample of 60 yabbies was taken. That's pretty good. That's pretty good, large sample size. The sample mean weight was 84.6 grams, so that's our X bar of 60 is 84.6. So we're going well. Find the 95% confidence interval for the population. Let's try to, population mean, let's try to trap the mean. If the population standard deviation is 16.8. Don't forget, that's a population mean. We're given that X bar is that's a population mean, so its sigma is sigma on root n for X bars. Remember, we're on a different curve now. I just want to reinforce this. If this is the population of weights of yabbies and the sigma mu we don't know, and the sigma of this is 16.8, then we're testing X bars. X bars are like this. Even if this is not normal, under the central limit theorem for an n of 60, we expect it to be centred around the same mean, which we're trying to capture. But the sigma, what's the sigma? The sigma of X bar is sigma on root n. The mu of X bar is the same as the mu of X. They line up. But look out, we have to test our X bar score on this distribution, not on the original one. We've given them 60 opportunities to get it right, if you like, and now we're going to test it. All right, so here we are. Here's the crucial line for the confidence interval. Don't forget these standard deviations are sigma on root n for an X bar distribution. Okay, putting the numbers in, 1.96 over root 60, all of these. Do it in run mode, and to 3 significant figures. We have trapped the mean. We are 95% confident that the population mean weight of yabbies lies between that and that. What would you put on the packet? Okay, if you were selling these frozen or something in a supermarket, what do you reckon you'd put? Okay, think about it quickly. I reckon I'd put 80 grams. And some people are going to get a big bonus here. But we'd be 95% confident that it isn't less than 80, so let's go for safety. We don't want Consumer Affairs investigating our product. Okay? So, think about that. You wouldn't go as high as that with your mean. You'd go for your 95% confident that somewhere in here, but let's go for safety. Quote, mean or average weight is 80 grams. Okay, all right. And you might work on the net weight, therefore. how many you've got in the packet, and the net weight would simply be the number of yabbies times that mean. Okay, because on the average that's what they would weigh. But go for the lowest one. So legally you're sure. Okay, have you got it? Getting the idea? Come on down now. Okay, here we are. The fat content in grams of 30, 30 is not bad, was determined and recorded as this. Okay, so the first thing we have to do is find the X bar of these 30. Okay, and here they've done on the calculator. How would you do that? What would you do? I haven't put the calculator up here. Stat mode, go to list, enter the data, set up calc on, let's maybe list 1, calc list 1, frequency 1, if you know the Casio, check it out, and then go and look at the first entry under calc for 1 there is X bar, and you could take it from there. Now, are we given? Yep, we're told that the population standard deviation is 1.35. But we are testing a mean. We've done 30 of them. 30 of them should be zeroing in on the population mean. Okay, by the central limit theorem, even if the original population is not normally distributed. So the mu of x bar is approximately under the central limit theorem, the mu of x, and this is narrower here. This is 1.96 sigma on root n, and neg 1.96 sigma on root n, or mu plus that distance there. Right, I haven't got room to do it. You know what we're doing. Here it is here. So mu is somewhere between x bar plus, so where's our x bar, plus the numbers, is between 15.4 and 16.4. So we're 95% confident that the mean fat content of all pasties produced lies between there. Now this time, what would you quote? Because you don't want fat in your pasties. So you might say that the average fat is less than, well, it could go up as high as 16.4. So should we say just 17? Okay, so that we have a nice round figure, and you're 95% sure of having a fat less than that. And so in a whole packet of pasties, the net fat would be the number of pasties times 17 grams, if you like, something like that. So if you are guarding against some prosecution due to a health problem, you might want to quote less than the highest value, but if you want to guarantee something else on the other end, then you might do the other end value. Depends on what you're trying to convey there. Okay. All right, come down, and do you want to have a go? Let's have a go at some problems. 7I1 here. There are 5 questions there for you. So pause the presentation in the usual way, and down below I'll show you the answers to these problems. Okay. Here we go. Oh, we haven't finished 5 there. Sorry, there's 5. Okay. And let's go down and look at them here. Can we get them all on? Not quite. Okay. Have a look. And we'll then go to 5. All right. Let's go down and have a look at what I've got here. I promised you I'd help you with technology here, and here it is on the calculator. Let's go through it. The Casio, you start off with selecting stat mode, hit execute, and then now this time it's different. The interval is under intra there, so you have to push F4, and Z comes up again, so it's F1, and one sample comes up, which is F1 again. And then we have this window. Okay, so here, see this confidence interval. You might have to scroll down and change that to, we could have a 99% confidence interval. That might be used for a higher accuracy. But in this course, it's always 95. Enter in the sigma of the population sigma, x bar n, so the calculator can adjust that sigma for x bar to sigma on root n. But it's a population sigma up here that you put in. What's this here? What's this? You need to hit F6 until you scroll right down to the bottom, which is this here then. Okay, so when you go right down to the bottom, you get to this, and there is calc there. So you have to hit F1. Okay, and if you hit F1, it calculates the confidence interval. One sample, left, right, reminding you that was your X bar and the sample size. Okay, so that's handy. You can do it all on the calculator. Just watch the wording of the question as to how much detail they want. I would always put in X bar minus 1.96 sigma on root n to validate your hang on, just do this, to validate your calculation, and even put the numbers in here. But for the actual calculation, then calculate it with technology for safety rather than in run mode, maybe. Okay, and to speed things up a bit. But I'd show the working leading up to it, and then do it on the calculator. All right, you want to do some, let's try here, a little variation on the problem here. A 95% confidence interval was calculated for a population, a mean, and a mean was put between those two. The estimate was based on a sample size of 60. Can you backtrack and find what was the sample mean? Well, let's write down the formula for the confidence interval, and we can say on one side it came to 8.5617, on the other side it came to that. And of course, that's equal, isn't it? X bar, the mu is between X bar plus and X bar minus, so that overall gap was 2 lots of X bar comes to that there. So you can actually add these up to get the deviation on either side. So X bar is 9. It's using symmetry. It's halfway between the two values. That's what we're saying. They're equally placed on either side. So if you get the total gap, the total, let's call it the total gap, then that's going to be 2 X bars worth. Okay. Now, what else can you do? Can you estimate the population standard deviation which was used to calculate the confidence interval? We're going backwards now. So you could use either of them here. We've got X bar minus 1.96 sigma equals the lower value, and therefore rearranging that, adding that across to both sides, subtracting that one actually from both sides, multiplying by -1, you can rearrange the formula to back estimate the sigma. Don't know why you do that, it's just an interesting result, I suppose, to say, well, we've ended up with a confidence interval for the mean. Can we estimate what the sample mean was and the standard deviation to start with? All right, so you might look at that. Let's have a look at some problems around that sort of thing. Here's a couple of them here. So 95% confidence, can you backtrack and find the sample mean, which is going to be the halfway between those two, if you like, and then the population standard deviation, so the same sort of problem. And then you can do the same thing here. What was the sample size? So you don't know n then. So just manipulating the same formula, X bar minus 1.96 sigma on root n, less than or equal to mu, less than or equal to X bar plus 1.96 sigma on root n. So playing with one of those expressions, you've got the you have to find X bar first, don't you? You have to find X bar by the same process and then use one of these to rearrange to get n. So have a look at that. All right, let's have a look at some problems. Solutions, sorry. Here we are. Here are the solutions. Okay, let's go on and see what else we can do. Exciting stuff trying to trap this mean and the various things we can find out about the population. Okay, so here, what if you're not happy with how big your confidence interval is? It's too big a range. What about determining a sample size or something like that? So here we are. Let's go back. There was an example earlier about the fat content of pasties. Now, could we answer this question? How many do we have to sample to find the population mean by less than 0.3 grams? Just keep in mind what we're doing this for. On the packet we want to say that the maximum fat content is such and such. Okay, and we don't want to be far out. So we want the difference between the actual mean and our sample mean to be no more than 0.3 grams. That's an overall width there of 0.6 grams. So that's what we're trying to put down mathematically. So we always go back to this 95% confidence interval. Let's subtract x bar from both of these, and we find that mu minus x bar, which is 0.3, must obey these things, or 1.96 sigma on root n must be greater than that, and minus it must be less than that. So we just take this one. This thing here, 1.96 sigma on root n, we want to find when that equals 0.3. We don't want any more. So we can solve that equation, and what are we going to do here? 1.96 sigma, rearrange this, put that up there if you like, multiply both sides by root n, divide by 0.3, so we get that, and then we would have root n is 8.82, so squaring it, n is about 78. You never use a decimal for a sample size, do you? You have to contextualise that mathematical answer, so you take it to the nearest one. So n is approximately 78. Or you could say, well, I'll take 80 pasties, something. So a sample of a minimum size of 78 pasties should be taken, and then we are 95% sure of being no more than 0.3 grams of fat out on either side there. Okay, so it's a differ from the population might mean by less than 0.3 grams. So study that. The crucial thing is, with this 95% confidence thing, we'll go straight to the confidence interval and try to work with that. Okay, come down and let's have a look at a problem. So we go back to our yabbies still swimming in the dam. Well, some of them are. We took out 60, but anyway, the rest are still swimming, I guess. Suppose we wish to find the sample size needed to be 95% confident that the sample mean differs from the population mean by less than 5 grams. So we start with that. Well, we really have started with a rearrangement of it. Mu take x bar will be between neg 1.96 sigma on root n and 1.96 sigma on root n, and so we want it to be less than 5 grams. So this deviation above or below is 5. So putting in the numbers and then multiplying across, divide by 5, and then squaring it, we have 43.37. So you have to round it to 44. Please contextualise your answer in the context. You can't have 43.37 yabbies. Okay, so you take it up. You can't take it down because then your accuracy will be lost. It has to be less than 5 grams, so you need at least 43.37, so that's 44. So that rounding up depends on the problem, of course. Here, you want a level of accuracy, you have to take more than the mathematical answer. Okay, practice this. Let's have a look. Here are 3 little problems for you. So pause the presentation, have a go. I'll come down and show you the answers now. I think we can get them all on there. Yep. So make sure you're rounding your answers to a practical contextual situation. You're sampling whole things. You can't have decimal answers. So check your answers then, and let's go on. Okay. Now, this is another variation. As I said to you before, what if you don't like, you've gone out and sampled 20 objects, and you don't like how wide this width is, wide this confidence interval is, the width. So you want it as small as possible. Now, to get it smaller, you're going to have to take a bigger sample size, and it will make it smaller, won't it? Because the width of this interval depends on 1.96 sigma on root n either side. So if we can make n larger, implies sigma on root n smaller, dividing by a larger number, implies a smaller confidence interval. Okay, we can actually make W as small as we like if we can afford to sample that many objects. Okay, so let's have a look at the mass of it. How big is this width? Well, the width is 1.96 sigma on root n on either side, so it's 2 times that. So let's rearrange it. This one, let's multiply both sides by root n, then divide by w, so we get a root n expression. And so n is the square of that. Hey, this is a powerful tool now, because if we want to estimate how many we have to talk to or measure or whatever, whether people or yabbies or some purple cow milk, then we can use this formula. We just specify how big we want the ending up confidence interval to be, and we go out and talk to that many people or measure that many objects. Let's have a look at it. Okay, so here's the result. When we used to estimate the population from a sample of size n at 95% confidence interval, it's all based on that 1.96 sigma on root n, so that's a 95% region, isn't it? Then the sample size is given by this, okay, which is just a rearrangement of that confidence interval width. Let's just check it now. X bar minus 1.96 sigma on root n. This is the important one, and it's between those limits with 95% surety or 95% confidence. Okay, so that's what's driving it now. Okay, so let's go down and have a look at a problem or two here. Question 4, 5 and 6, I'd like you to have a look. Can you see what we're doing? It is important. We're trying to set up a survey or a sampling process where we know that we will come out with a reasonable size confidence interval. We won't have to go and do it again. Saying, well, that's not specific enough. That's too broad. We want a better idea. So we're setting up how to get that good mu trap. Remember this, a mu trap. We're trying to trap the actual mean of the population with 95% surety. Okay, have a go at these. I'll show you the answers now. Okay, and there are the answers. Check it through, and just remember, make the answer in context. You can't be sampling a decimal number of objects. Okay, and you must have at least the value that you've come up with to ensure that you keep the level of accuracy of 95% probability. Okay, let's go on. What else can we do? There are a couple of other little things in this hunting for mu. Oh, here it is. The protein bar's back again. I thought you ate all of those. Oh, well, anyway. What we've got here, 27 grams of protein. Also, they've got a net weight down there as well. How can you check that out? Okay, well, we had the hypothesis test, didn't we, where we sampled and went through that. Well, this is a version of that. This is less formal. We can say with 95% confidence that when we sample these bars and get an X bar there, a mean protein weight, let's check the protein content. Okay, then the actual mean, which should mean 27, lies somewhere in those limits. Otherwise, we're going to question that statement there. If it's a claim about mu, and all products have a claim about their mean. Why is it a claim? Because you can't measure all the bars to get the population mean, because there'd be nothing to sell, mate. Okay, so we're going to go out and get X bar. X bar will be under the central limit theorem, approximately, it's going to be distributed normally with a mean of the population mu and sigma on root n squared. Okay, by the central limit theorem. If n is sufficiently large, okay, make sure n is sufficiently large. Okay, and we can make up a confidence interval and check out this 27 grams. It should lie within there. Otherwise, we can be 95% sure that that claim on that packet is incorrect. How powerful is this? This is actually used by Consumer Affairs in the Trade Measurement Act to check things out. Because in the Trade Measurement Act, it says that if you take a single item, then it can be up to 5% less. Must be within 95% of what's published. if you take 6 or more, then they have to be greater than or equal to the labelled weight. Okay. So they're using the central limit theorem. I mentioned this before. So that's the idea. We go out and sample, construct a confidence interval and state that with 95% confidence we can accept that that is the mean or not, or that is reasonable to mean. Remember, we can't actually validate 27. It might lie within our confidence interval, so we can say, well, they're not wrong, but we can't say absolutely that it's 27. This is the area of probability, isn't it? Okay, so let's come down and have a look at an example now. Volume V of cool drinks dispensing to carton by machine, normally distributed with mean mu. Cool drinks, I like Purple Cow, which can be adjusted, and standard deviation 10 mils, which is fixed, so the mean can be adjusted. The value of mu is supposed to be 1005 mil, but the machine operators notice that it's actually 995. The operator therefore adjusts the volume, and a controller then comes out and tests 25 cartons, finds that the mean is 1007. Now, well, with the volume dispensed, it's probably going to be random variation, and therefore the volume will be normally distributed, and the mean will be, but 25 cartons, yeah, it's a bit small, but let's say CLT applies, okay, because n20 equals 25 is approximately, is large enough. Now, let's have a confidence interval. So, what do? Construct an n95% confidence interval. Well, what have we got? We've got the x bar is equal to 1007, n is 25, and the sigma was 10 mils, so sigma on root n is 10 on root 25. Well, that's going to be 2 if you're doing it by hand, or they've just gone straight to the calculator. And remember, on the calculator you're going to feed in 0.95, and then the sigma of the population, which was, what is that? Sigma is 10, n was 25, x bar was 1007. Okay. So they're saying now you get this confidence interval, and what we're going to say, can we test the claim? Well, since 995, okay, that's what the operator noticed, 995 is less than all the values, we can be confident that the population mean has increased. The operator adjusted the volume, and did it go up? Yep, because 995 is no longer in that interval. Okay, so it has increased, because the interval is above 995. Now, although, spelling error there, although the sample statistic 1007 mils is greater than 1005, which is what it was supposed to be, the smallest number could be 1003. So we can't actually say that this confident interval says that it's gone up from 1005. Now, just we'll look at that. Come back up here. There's gone out and got 25 cartons. By chance, their average is greater than what we require. And most people would say, oh, it's gone up. See, it's bigger than what we require. It's okay. But actually, we can't say it's any more than 1003, because we're sampling, there's random variation there, and just because our sample is above what was required, it may not be the regular thing. It could be as low, here it is, as 1003. So we may still not be fulfilling the idea of 1005. So get that idea of random variation. So here, this means that mu could be as small as 1003, and there's not enough evidence to support the claim that it's gone up above 1005 or up to 1005. It could be, because 1005 is in here, but we can't actually state that. So this is exactly the same idea. It's the same maths. It's closely related. It's a different format using the mathematics here. We're doing it with a confidence interval. Okay, the same idea of that region of the curve within which we will say accept the null hypothesis, and outside of which we would reject it. All right. Let's have a look now down at some problems on this one now. 7I3, a few little problems there. There's question 1 and 2. And pause that, and then let's bring up 3. But A and B, and have a go, think about it. Okay, I'm going to go down and show you the solutions now. I think we can fit them all on. Yep. 1, 2 and 3. All right. There are a couple of little things still to do. Let's come down and see what we can do with them. Other applications of confidence intervals. Now this is very, very important. Let's study this carefully. Now, a buyer goes to a seafood wholesaler who's got a catch of 50,000 prawns. She has instructions to buy the whole catch, only if the prawns are heavy enough. You can't measure 50,000 of them. Pretty smelly exercise as well. Better use gloves for that. The buyer selects a sample of 60 prawns and finds their mean weight is 57.2 grams. The population standard deviation is 4.2. You might ask, how do they know that? Anyway, let's accept that. Find the 95% confidence interval for the population mean. Okay, using technology now, we go from 56.1 to 58.3. You could check that with a hand calculation as well if you wanted to. So, what are we saying? Is that heavy enough? Their mean weight was 57.2, but overall that meant the mean of the population could be as low as 56.1. All right. The smallest value is 56.1, so the buyer can be 95% sure the population mean is greater than the lowest value. Okay, now what are we going to do here? She's 95% confident no more than 10% weigh less than 50. Oh, now this is getting interesting. 95% confidence, that's something to do with the confidence interval, that no more than 10% weigh less than 50 grams. Use the confidence interval to justify this claim. There's a lot of maths there. So first of all, what are we saying? No more than 10% of the prawns weigh less than 50 grams. We're saying now 50 grams. What is the proposed mean here? The proposed mean of the original population is 56.1. We can't use 58.3. It may not be up that high, but we know it's going to be, at least with 95% confidence, at least 56.1 grams. Okay, so let's go for the lower limit. Then what's the probability of getting prawns less than 50 grams? So we're talking about the prawn weight being normally distributed with a mu and sigma. Mu, take the lowest one, so we're sure, and the sigma is 4.2. I'll write that over here. And 95% confidence comes from the fact that we're working on the lowest level of a 95% confidence interval. So it can't get any worse than that. We're 95% sure, therefore, that that's going to be the mean of the population, and we want to know, if that's the case, what is the probability of getting a prawn less than this? This is the actual X distribution now. Okay, 56.1 and 4.2 squared. Okay, so what's that probability? Let's go into the calculator and use NCD, and we come up with 0.0732. So therefore, yes, it is less than 10%, weigh less than 50 grams. So just get that idea. And of course we might want to use the upper level of a confidence interval if we want to say we're sure that there's no more than 58.3 grams of fat in something, because in fat you don't want it. In the weight of a prawn, yes, you do want it. So you could be using either end of the confidence interval. So watch for the key words there. The 95 up here, the 95% confidence suggests something about a confidence interval. You pluck the mean out of that, and you don't want any more than, so you want the least mean, and you want the probability less than 50 grams to be 10%. So you can go and check it. This is the difficult thing about this course. Some of the wording and just to unravel all the probability statements can be difficult. Underlining things, drawing little pictures like this about what's really going on helps your problem solving. Okay, let's go down and do a problem or two on this one. Okay, so we've got 2 questions there. So check it out, think carefully about using the confidence interval to estimate an upper or lower possibility for the mean, and then to work out some probabilities with that. Okay, I'm going to show you the solutions now. Come down, and there are the solutions to those 2 problems, and see what you think. Alright, one last bit. Hope you're not getting too tired. We haven't got any protein bars or drinks left. Sorry about that. Extension to confidence intervals other than 95%. This is rare. No, we don't do this much in this course. You could want a confidence interval of 99% or 90%, and you would generally use your calculator technology. Okay. If you want to test a little bit of your statistical knowledge, then you might do this without a calculator, and you go back to the standard normal curve to work out that 1.96 on either side, or it would have to be bigger than that for a 99% confidence interval, and then this is what this question's about. The A value is the number of standard deviations on either side to get that middle value, so A is 1.96 for a 95% confidence interval. So you could do all of this using the Z distribution, okay, and it will vary. Alright, see what you think of all that. I'm going to take you down to the answers now. Okay, so here are the final problems, and this does wrap up inferential statistics in this little course, and we'll be doing some more presentations on the binomial probability function, but at the moment, keep working hard. Congratulations on getting to this point, but for now, it's cheers from me.